Okay, so let's begin. When a computer does this, to me, I usually get disappointed. It's a computer, right? It should have been designed to do computations, right? So what's wrong with it? We'll look at some of the issues and what we can do about it. Hello, everybody. My name is Martin Becker. I'm a mathematician, and I work in quality assurance, among other things, of course. So I like good software. I also happen to like Perl, which is why I'm here. And this is not necessarily the same. Larry is not here with us, but he had that coming. So what do I mean with precise math? To the left side, this is pocket calculator stuff. It's about approximation. And what I want to talk about now is the right side, things that we might be inclined to prove as a fact. Just like this identity that has been discovered by Carl Friedrich Gauss 200 years ago. And if you write software that can deal with square root expressions, this is the real part of the 17th root of unity. And if you take that root to the 17th power, you give your math system something to do. And I'd like to see the output. So we are talking about software that can handle mathematical entities precisely, correctly, hopefully. Some of these programs come with additional bells and whistles, like being able to deal with arbitrary symbols. Or can in any way carry mathematical facts through a calculation. The larger systems of this kind we call computer algebra systems. There are more than I've noted here. What is special to them is usually you have to pay to use them. The exceptions are this on the right. Maxima is a very old system, or comes from a very old system that got open sourced at its 30th birthday in 1998. And Sage Math is an effort to combine many existing open source libraries such as GMP, the new multi-precision math library, Pari, Maxima, SymPy, you name it, with a long-term goal to be able to compete against the commercial systems. So why should we do this in Perl? There are a number of reasons. Not the least of one is the one below here. We are Perl programmers and we like to do things in Perl. Perl has had useful features for a long time that appeal to mathematicians, such as object orientation and operator overloading, not to mention a rich set of operators to overload. Before Perl 6 came along, Perl was famous for its operators, while now it looks somewhat poor and incongruous in comparison, but we should prefer well-named methods, probably, anyway. Why Perl 5, you might ask, since nowadays there are two languages. sharing a first name. And one thing that stands out is that Perl 6 doesn't, at least now, have the same reaches out to the same number of systems. And of course, we will do the good stuff in Perl 5 and Perl 6. So what kinds of mathematical objects are precisely representable? For one thing, there are integer and rational numbers for lack of rounding errors, where computers can deal with them without introducing errors just through rounding, because there aren't. Then we can take a look at elements with finitely many instances, all sorts of them. And these, in turn, we can take as coordinate space for for structures that are built on top of them, like vectors, matrices, elliptic curves, projective planes, you name it. Let's start with integers. These have been in Perl for a very long time. As long as Perl 5 exists, the module math big int exists, and this has made it possible to deal with integer numbers that exceed the word size of your system. As for software qualities, it still leaves room for improvement. We'll see examples in a moment. Other solutions providing integer math include these. For example, the GNU multi-precision library comes with an own module GMP with Perl bindings. It works. You won't get it installed on very new Perls because they deprecated some constructs they employed, but it would be easy to fix, easy enough. But there are also several CPAN modules with the same scope, math GMPZ being the more advanced one. However, this is not very user-friendly. For example, if you don't do your share in memory management, it will just crash your program. And the bottom one here, math big num, looks somewhat promising. It is a nice wrapper from math GMPZ and its companion modules. The drawback here is that it has one type and one numeric type that should fit all. So you can start with an integer and employ a transcendental function on it, and suddenly you have a floating point number. Whereas we like to be a bit more strict sometimes and know when we want this and when that. Which brings us right to the rational numbers. These have also a module that is in a core, Perl core distribution. It's math big red. It has had its good share of bugs and idiosyncrasies. And please don't misunderstand me. I don't want to bash the maintainers of these modules. Some have such a long history that it takes really an heroic effort to bring that up to speed and to quality. And it's just not perfect what I had to start with. One thing that was particularly difficult to live with was what I call the math big red trap. The big red trap. It goes like this. You start with fairly recent Perl and the big number modules it brings with them. Then, intentionally or not, you upgrade your math big int, and suddenly your math big red will stop working. But in a subtle, annoying way, not just core dump on your thing or break it, it will silently give you wrong results. And this is what I hate most in math modules. Initially, I said we would like to treat what they tell us as mathematical proofs. And you will have a hard time to prove that 2 plus 2 is 5. And that's a problem. The big math, the big red trap. What, of course, you should do to repair this is to upgrade math big red after you have upgraded math big int. Unfortunately, our toolchain will not do that for us. But if you make excessive tests, you will finally find it out. Other examples for problems to live with these modules include that it can take very long to repair easily spotted mistakes. The second one is something of math big float, not my focus here, but to show you the dimension of what happens here. We all know trigonometric functions like the sine wave. It is periodical in theory. With this module, it's not periodical and it diverges towards infinity. Or it doesn't because it takes forever before it gives you a result. And lots of other yet unfinished issues. Well, this one should take the biscuit. The variable y gets changed purely because it is involved in some other expression. This obviously shouldn't have happened, and it was easily enough fixed. Unfortunately, it didn't make it into Perl 5.26, certainly in 5.26.1. But I want to highlight the root cause of this. This family of modules goes a long way to make objects, standing in for numbers, mutable, so that you can say A is incremented by some value, and as you are going to throw away a previous instance of A, just as well can recycle this object and store the result in A. And this is what happened in this bug. Some internal function was calling a method that would change its argument where it shouldn't have. And the quintessence is that you should make objects that take part in expressions and stand in for numbers and so immutable. With this design, it's easier to get right. Whenever a new value comes out, a new object is created. And you can use your references to the old objects and never be surprised. The internal architecture of these three modules is surprising because big float is a big int and big red is a big float, at least this is the inheritance hierarchy, but either itself is overloaded to tell you, no, I'm a separate module. And more logical would maybe be the other way around, or Peter intends to refactor it into such a structure. We have common code and 3 different modules that inherit from that. That will be easier to maintain. So, some lessons learned here. For module authors, how could you make changes hurt less? We want to help our users, don't we? For one thing, I'm a big fan of when I introduce new functionality, I do this preferably with new methods, with new names for things. So the old ones and the new ones can probably coexist. Or if I really want to get rid of what the old method did, I can do this and orchestrate some sort of deprecation process. First tell people that it's just better to use the other thing, then probably make it a configurable warning if you use it still, and only finally at the last stage, when enough time has gone by, really remove that. And when you decide to break things, which is important because we want to make progress. If it was stupid, we don't want to continue that. If you decide to break things, break it in a way that is obvious. So if your program crashes with lots of fanfare, you can tell there is a problem. And you won't get trapped into believing it is ready and done, and where into what comes out is just plain stupid. For module users, how to cope with changes. Look out for your reverse dependencies. As I said, the toolchain won't do that automatically for you. Of course, you can employ meta-cpan and look reverse dependencies up, but these are only those that are also on cpan, not in your own module infrastructure. Perform tests, regression tests, and as if things break that worked before, dig that out and look for deprecations that are actually advertised. Let's glimpse into what other languages do. Perl 6 also has integers and rationals. Rationals actually 2 kinds. The red type is supposed to automatically degrade its object to num. That's a limited size floating point when the denominator exceeds 64-bit. That sounds somewhat arbitrary. We should keep in mind that all 3 of those, integer red and fat red, will happily eat every bit of your space and more. They are not nice to work with. Just keep calculating with them, and you can't control the amount of space they take. In case of red, you need the part. You need the integer part to get larger. And what would have been nice was some sort of exception you can catch when a certain size limit is reached by the number itself, not by the program in total. On the other hand, it's very nice that integer is deeply integrated in the language and not just a module, because it's easier to include it in application code. Python 3 has also from the start had big integers and also fractions, which are our rationals. Unfortunately, it's not very performant. It's mainly written. It's mainly Python libraries written in Python, and it has a quite impressive symbolic math library, which works very well. And the expression I mentioned in the beginning with the square roots took 38 minutes on this laptop to expand. So we can look up interesting algorithms there and should implement them in some more efficient way, and then we're done. So much to rationals and integers. Other object types. I'm sorry if this gets a bit mathematical. We have a lot of stuff on CPAN that can already provide this functionality. Modular integers are there in math_mod_int, math Galois field, or finite fields I'm at the moment working on. Then we have polynomials. Matrices are not yet complete, and I'm not sure if the author is intending to do so. Then we have elliptic curves in lots of modules, but not as a module of their own. And I'd like to have that as something that can be orthogonal to the rest. So you can have elliptic curves over finite fields, for example, or matrices of elliptic curves elements, whatever. Then symbolic math has a module, but it's more a toy, not like SymPy, a real full-blown symbolic math library. And we have, for the integer functions that are missing in math_begin, we have math_prime_util. The drawback of this module is that you have you need other libraries for it to run, or at least for it to run efficiently. But they are also there. To conclude, we really should reserve the math namespace for earnest mathematics that doesn't cheat and give us nonsense. So make correctness a top priority. Nobody's perfect, there will be bugs, but it's you should care. At least you should care, so that these bugs get fixed. And then I would wish, in Perl as well as in other languages, that I had types for large numbers with a configurable size limit. I can catch as an exception. And so when my program runs and gives a result, I know it's correct. And otherwise, it might tell me, I ran out of space. Give me more space and you might be good. This would greatly aid application development. Then I doubt the idea of automatic downgrading. In the documentation, it even is called upgrading, but you can't downgrade a 1,000,000-bit number to a 64-bit number. This is downgrade, not upgrade. And it may be helpful in not crashing your program, but it hurts the truthfulness of your output. And of course, application developers should be aware of the risks that are involved with unlimited sizes. And last but not least, a number like objects. Objects meant to be part of expressions and used as mathematical symbols should probably be immutable. So that was it so far. Question or comments?
I'm curious how you would deal with a rational number. If there was any need to use, say, something like pi or d.
The question was, how do you do rational numbers? Is it
irrational numbers?
Irrational numbers. Okay. Irrational can be everything. It can be transcendental or whatever. And of course, we have in a finite system like a computer, no way to exactly represent every irrational number. On the other hand, if it's a known symbol, for example, the square root of 2 is irrational, but I can exactly tell what its properties are. I can do the same thing that a mathematician does on pencil and paper with it. Software can do that too, and can keep it correct. What you do as a rule is you have an expression and model this expression as a sort of a tree, and certain rules that can be applied will rebuild your tree or simplify your tree. And as long as you're on the turf of mathematically sound operations, you will have symbolic math or irrational numbers, not spelled out in digits, but as something that is well defined.
Are there libraries for symbolic integration and differentiation?
The question was, are there libraries for symbolic calculus? There are. It depends a bit on what functions you want to integrate. If you want to integrate arbitrary expressions, something like math symbolic will help. If you just want to integrate something like polynomials, math polynomial will already do the trick. And if you are into a heavy-duty integrating, you probably have to use an interface to an external library, like MathParry, for example, Parry GP. Over there.
What is your opinion on the PDL? Is it doing the same thing or different?
The question was what is my opinion about PDL? PDL is a Perl short for Perl data language. It's a Perl module. Its main focus is to handle lots of data efficiently, because some of the layers to make it Perl, some of the layers that would come from wrapping Perl scalars into matrices and vectors are not necessary. So PDL is very well to handle lots of data that comes in vectors and matrices, but this is not intended as a high precision language or high precision math library, because those primitives are still Perl scalars, so single or double precision floating points. So it has its Nike in the infrastructure, but more for mass data than for especially big numbers or something. May I ask questions? Are there module developers among us? So we represent more of the user community, which is fine by me, because even if you don't intend to make the product better, you should know how to use it and where its limitations are. So I hope you enjoyed this and could get something of it. Thank you for your presence and